We have not built a spacecraft that can carry humans beyond the moon in over 50 years. Despite decades of progress, humanity is still a single-planet species, held back by a series of unsolved technological bottlenecks. By the end of this video, you will see the 24 engineering and scientific barriers that must fall before we become a true spacefaring civilization. What makes the rocket equation so unforgiving? Why can't we simply recycle air and water with perfect efficiency for a multi-year mission? Which of these bottlenecks do you think is the hardest to overcome? The rocket equation is a ruthless mathematical law that punishes every gram of ambition. To send a single kilogram of payload beyond Earth, you must burn dozens of kilograms of fuel. And to go further, that ratio grows exponentially, not linearly. This is the tyranny of the rocket equation, and it shapes every mission to the Moon, Mars, or anywhere beyond low Earth orbit. At its core, the equation is simple. The faster you want to go, the more propellant you need to carry. But that propellant itself has mass, so you need even more fuel to lift that extra weight. It becomes a spiral where small increases in final speed demand massive increases in starting mass. For a spacecraft traveling to Mars, about 90% of its total launch mass is propellant. Only a tiny fraction remains for the crew, life support, instruments, and everything else. Consider the Saturn V rocket, the most powerful ever built. It stood over 300 feet tall and weighed nearly 3,000 metric tons at liftoff. Yet the payload it sent to the Moon, the command module, service module, and lunar lander combined, weighed less than 50 metric tons. That is less than 2% of the total launch mass. The rest was fuel and structure needed to burn that fuel. Every inch of that journey came at an enormous cost in propellant. Now look at Starship, the next-generation vehicle designed for deep space. Its engineers face the same equation. To send humans to Mars, Starship must carry enough propellant not just to get there, but to slow down, land, and eventually return. That requires refueling in orbit because the equation makes it impossible to launch from Earth with everything on board. The vehicle must stop at a propellant depot in space, transferring hundreds of tons of methane and oxygen from tanker ships. Without that orbital refueling, the payload to Mars would be nearly zero. This single physical constraint forces every deep space mission into a brutal trade-off. Do you send more people or more supplies? Do you add radiation shielding or save weight for life support? Do you take a faster trajectory that burns more fuel, or a slower one that extends mission time and risk? The rocket equation offers no mercy. It sets a hard ceiling on what is possible with chemical propulsion. And that is why the first bottleneck on the road to a spacefaring civilization is not a computer chip or a new material. It is a formula written over a century ago by a Russian schoolteacher named Konstantin Tsiolkovsky. His equation still determines the size, cost, and feasibility of every mission we dream of. Until we break free from its grip, we remain tethered to Earth by an invisible chain of mathematics. The real limit of chemical propulsion is not just weight, but speed. Every chemical rocket engine, no matter how advanced, is trapped by the energy released when fuel and oxidizer combine. That energy sets a hard ceiling on something engineers call specific impulse, which is a measure of how efficiently an engine uses propellant to produce thrust. For the best chemical engines, like the hydrogen-oxygen systems used on the space shuttle or the upper stage of the Saturn V, specific impulse peaks at around 450 to 500 seconds. That number has not budged in decades, and it never will because the chemical bonds themselves cannot release more energy than they hold. What does that mean in practical terms? It means that even with the most energetic propellant combinations, a spacecraft can only change its velocity by a few kilometers per second before it runs out of fuel. To reach Mars, you need about 3 to 4 kilometers per second of change. To reach Jupiter, you need nearly 9 kilometers per second. To reach Saturn, even more. And because the rocket equation punishes every extra kilogram of propellant, the amount of fuel required to achieve those higher speeds becomes astronomically large. The result is painfully slow travel. A chemical rocket sent to Jupiter takes about 6 years. A trip to Saturn takes nearly 8, to Pluto more than a decade. These are not journeys for crews. They are long, cold drifts through empty space with only a brief flyby at the end. Consider the Voyager probes. Launched in the late 1970s, they used gravity assists from Jupiter and Saturn to gain speed. Even then, it took them over 12 years to reach Neptune, and those were small, robotic spacecraft with no life support, no crew, no need for food or water. They could coast for decades. A human mission cannot. The human body deteriorates in microgravity. Bones lose density, muscles atrophy, radiation exposure accumulates. A 6-year journey to Jupiter would be a death sentence before arrival. So chemical propulsion does not just limit speed, it limits the entire architecture of exploration. Every planet beyond Mars becomes unreachable for humans unless we accept transit times that stretch into decades and survival chances that shrink to zero. This is the second bottleneck. The rocket equation dictates how much fuel you need. Chemical-specific impulse dictates how fast you can go. Together, they create a cage that holds us within the inner solar system. We can send robotic scouts to the outer planets, but we cannot follow them. And that gap will only close if we find a way to burn propellant more efficiently or abandon chemical reactions entirely. But before we consider alternatives, we must first understand another deep limitation: the fragile and unforgiving nature of human biology in space. The human body is not built for space, and the limits of chemical rockets cannot get us where we need to go fast enough. So engineers have spent decades searching for a better way to push a spacecraft forward, and one of the most promising candidates is nuclear thermal propulsion. The idea dates back to the 1960s, when NASA and the Atomic Energy Commission ran a program called NERVA, which stands for Nuclear Engine for Rocket Vehicle Application. The principle is simple and elegant. Instead of burning chemical fuel, a nuclear reactor heats a propellant, usually hydrogen, to extremely high temperatures. The hot gas then expands out of a nozzle, producing thrust. Because nuclear reactions release far more energy than chemical ones, the specific impulse jumps from around 450 seconds to roughly 900 seconds. That is effectively double the efficiency. A nuclear thermal rocket could cut travel time to Mars from 9 months to 3 or 4 months. That is a game changer for crew safety. Less time in microgravity means less bone loss, less muscle wasting, and a smaller radiation dose from cosmic rays. So why don't we have nuclear rockets flying today? The answer is a tangle of technical, material, and political problems. First, there is the weight of shielding. A nuclear reactor produces intense radiation that would destroy electronics and harm astronauts. To block it, you need thick layers of lead or hydrogenated materials, which add many tons of mass. That extra weight partly cancels the efficiency gain from the higher specific impulse. Second, the reactor materials themselves must survive extreme temperatures and intense radiation. The fuel elements need to withstand thousands of degrees without melting or cracking. The NERVA program solved some of these problems with graphite-based fuel, but the test engines had limited lifetimes and occasionally suffered from erosion and vibration. Scaling up to a flight-ready engine that could run reliably for weeks or months remains an unfinished challenge. Third, and perhaps most significant, is the political and regulatory resistance. Launching a fission reactor on top of a rocket makes many people uneasy. the risk of a catastrophic failure during launch, where the reactor could break apart and scatter radioactive material across the ocean or over populated areas, has been a persistent barrier. No government or space agency wants to be responsible for a nuclear incident in the atmosphere. In the United States, strict environmental reviews and public opposition have kept nuclear thermal propulsion grounded for decades. The NERVA program was cancelled in 1972, and since then only a few small research efforts have kept the concept alive. Even today, as NASA explores nuclear concepts for lunar and Martian missions, the regulatory hurdles remain enormous. The design must include multiple safety systems to prevent a reactor from becoming critical during a launch failure. That adds complexity, cost, and weight. And despite the promise of cutting travel time in half, the gap between a ground test and a flight-ready engine is still wide. Nuclear thermal propulsion offers a real step forward, but it is not a silver bullet. It solves the speed problem without solving the rocket equation entirely. You still need to lift the reactor, the shielding, and the hydrogen propellant into orbit. And hydrogen is notoriously bulky and difficult to store for long periods because it boils off over time. So while nuclear rockets could open the inner solar system to faster crewed missions, they do not break the fundamental constraints of mass and distance. They are a bridge, not a revolution, and they bring their own risks that unsettle both engineers and the public. So where do we turn next if we want to go truly far? Not just to Mars, but to the outer planets and beyond. That question leads us toward an even more ambitious technology. That question points toward a fuel source that powers the stars themselves. Fusion propulsion promises specific impulse measured not in hundreds or thousands, but in tens of thousands of seconds. A fusion rocket could theoretically reach Mars in weeks, Jupiter in months, and Saturn in under a year. It would open the entire solar system to human exploration, not just the nearby planets. The potential is staggering, and that is why engineers have chased this technology for over 70 years. The core idea is simple. Take two light atomic nuclei, force them together under extreme heat and pressure, and release the binding energy that holds them apart. That energy is millions of times more efficient per kilogram than chemical reactions. In a fusion engine, the exhaust would be a stream of superheated plasma moving at thousands of kilometers per second. That velocity translates directly into the specific impulse that makes other propulsion systems look like horse-drawn carts. So why is fusion not powering our spacecraft today? The answer lies in the immense difficulty of controlling a miniature star inside a vehicle. To achieve fusion on Earth, you need to heat hydrogen fuel to over 100 million degrees Celsius, hotter than the core of the Sun. At those temperatures, matter becomes a plasma, a soup of charged particles that wants to expand and cool instantly. Holding that plasma stable and dense enough to sustain the reaction requires powerful magnetic fields or intense laser compression. Magnetic confinement, the approach used in tokamaks and stellarators, has been studied for decades, but the magnets and the support systems needed to create those fields are enormous, often weighing hundreds of tons. Scaling that down to a flight-weight reactor is a massive engineering challenge. The magnets themselves must be superconducting, which requires cooling to near absolute zero, adding yet more complexity and weight. There is also the problem of energy break-even. No fusion reactor built so far has produced more energy than it consumes. The record set by the joint European Torus in the late 1990s achieved a Q value of about 0.6, meaning it output 60% of the energy put in. That is a remarkable scientific achievement, but it is not enough for propulsion. To power a spacecraft, you need a reactor that generates a net surplus of energy, and then you need to convert that energy into thrust efficiently. That second step is itself a separate challenge. One promising concept that tries to address these hurdles is the direct fusion drive, developed by Princeton Satellite Systems. It uses a field-reversed configuration, a type of magnetic confinement that is simpler and more compact than a tokamak. The idea is to inject fuel in a ring-shaped plasma and then compress it with magnetic fields until fusion ignites. The resulting high-energy plasma is then directed out of a nozzle to produce thrust, while some of the energy is tapped for electricity to run the spacecraft. In theory, a direct fusion drive could produce both propulsion and power, making it a dual-purpose system. But like all fusion concepts, it faces the same fundamental gap. It has not been demonstrated at a scale that can fly. No sustained, net-positive fusion reaction has ever been achieved in a reactor that could fit inside a rocket. The fusion community is making steady progress. Tokamaks like ITER aim to demonstrate net energy by the mid-2030s. Private companies are pursuing alternative designs using newer magnet technology or different confinement schemes. But a flight-weight fusion engine remains a breakthrough away. The materials needed to withstand the neutron flux from a fusion reaction are still under development. The control systems that can stabilize a plasma for hours or days in a moving spacecraft have not been built, and the regulatory and safety hurdles, while less severe than with fission, still require extensive testing to prove that a fusion rocket will not fail catastrophically. For now, fusion propulsion sits in the same category as clean energy on Earth. It is the holy grail, endlessly promising but always just beyond reach. Every year, researchers push the record for plasma temperature, confinement time, and energy output a little higher, and one day, those incremental gains may cross the threshold into a practical engine. But until that moment arrives, the solar system remains locked behind the slower, heavier doors of chemical and nuclear thermal rockets. The dream of a fusion-powered spacecraft is not dead, but it is waiting for a single, decisive breakthrough that will change everything. Beyond fusion lies a realm of propulsion that reads like science fiction. Antimatter, beamed energy, and warp drives are names that spark the imagination of every space enthusiast, but they remain firmly in the realm of theory, with engineering hurdles that dwarf even the fusion challenge. Antimatter engines would work by annihilating matter and antimatter together, converting mass directly into energy with 100% efficiency. A single gram of antimatter could produce as much energy as a nuclear bomb, and a spacecraft carrying just a few grams could reach Mars in days instead of months. The problem is that antimatter does not exist naturally on Earth in any useful quantity. We produce it in particle accelerators, but at a rate of less than a billionth of a gram per year, and the cost is astronomical, trillions of dollars per gram. Even if we could make enough, storing it is a nightmare because antimatter annihilates upon contact with ordinary matter. It must be held in magnetic traps which are heavy and require continuous power to maintain. Any failure in the containment system would result in instant destruction. For now, antimatter propulsion is a tantalizing idea without a practical path. Beamed energy propulsion offers a different approach. Instead of carrying fuel, a spacecraft would receive energy from an external source, like a ground-based laser or a microwave transmitter. The energy heats a propellant or directly pushes a reflective sail, eliminating the need to lift the fuel. This concept is already being tested with small solar sails, but scaling it up to human missions faces immense difficulty. The beam must stay focused over millions of kilometers, which requires enormous mirrors or phased arrays that have never been built. The beam itself would carry enough energy to vaporize anything in its path, raising obvious safety concerns. And the power required to accelerate a crewed ship to useful speeds would be measured in gigawatts, exceeding the total output of many nations. Despite these challenges, beamed energy could one day enable interstellar probes that travel at a fraction of the speed of light, reaching nearby star systems in decades rather than centuries. Then there is the most speculative concept of all, warp drives. Inspired by the Alcubierre metric, a warp drive would compress spacetime in front of a spacecraft and expand it behind, allowing the ship to effectively move faster than light without violating relativity. The idea is mathematically plausible, but the energy requirements are staggering. Early calculations suggested that a warp bubble would need the mass energy of a planet, compressed into exotic matter with negative energy density. We have no idea how to create or manipulate such matter. Later refinements reduced the energy demands, but still to levels far beyond anything humanity can produce. Warp drives remain a pure thought experiment, a reminder that physics may allow things we cannot yet engineer. These exotic concepts should not distract from the nearer-term solutions that could open the solar system within our lifetimes. Chemical, nuclear, thermal, and even early fusion engines are achievable with current or near-future technology. The exotic ideas are like the distant stars in the sky, beautiful to look at, but not a place we can reach yet. Still, they hold a crucial role. They push the boundaries of what we consider possible, and one day, a breakthrough in fundamental physics or material science could turn one of these dreams into a workable engine. For now, they remain the frontier of human imagination, a promise of what might come after we conquer the nearer horizons. There is another path that avoids the rocket equation entirely, but it comes with its own set of trade-offs. Instead of carrying fuel and blasting it out the back, a spacecraft can push against an external source of momentum. Solar sails use the gentle pressure of sunlight itself. Photons from the sun carry a tiny amount of momentum, and when a large reflective sail is oriented to catch them, that momentum transfers to the spacecraft, giving it a slow but constant push. No propellant is needed, no heavy tanks, no combustion. The sail is lightweight and can be deployed once in space, and because the push is continuous, the spacecraft gradually accelerates over weeks and months, eventually reaching much higher speeds than a chemical rocket could manage on the same mission. The concept has been tested on small-scale missions like the Japanese Ikaros probe and the Planetary Society's LightSail, which proved that sunlight can indeed move a spacecraft. But here is the catch: the pressure of sunlight is incredibly weak. At Earth's distance from the sun, it delivers only about 9 micronewtons per square meter of sail. That is roughly the weight of a grain of sand. To get any useful acceleration, the sail must be enormous, often covering thousands of square meters, and the spacecraft itself must be extremely light. A solar sail could take years to accelerate to high speed, and it cannot carry heavy payloads. A crude habitat with life support, shielding, and supplies would be far too massive for a sail of any practical size. Solar sails are best suited for small robotic probes or for missions that require long, gentle travel, like exploring the outer solar system or station keeping near the sun. They are also limited by distance. As you move further from the sun, the light pressure drops with the inverse square of the distance. Beyond Jupiter, sunlight becomes too weak to provide meaningful thrust. So solar sails are a clever solution, but only for a narrow set of missions. The other major propellantless option is electric propulsion, often called ion thrusters. These engines work by ionizing a gas, usually xenon, and then accelerating the charged particles through an electric field. The exhaust velocity can be extremely high, up to 50,000 meters per second, which gives an ion thruster a specific impulse of 3,000 seconds or more, far beyond chemical or even nuclear thermal rockets. That means an ion thruster uses propellant incredibly efficiently. A small tank of xenon can provide a massive total change in velocity over the life of the engine. The catch is that the thrust is minuscule. A typical ion thruster produces only about 90 millinewtons of force, roughly the weight of a single sheet of paper. A spacecraft using ion propulsion cannot lift off from Earth. It must be launched by a chemical rocket into orbit, and then its ion engine can start pushing. But the acceleration is so gentle that it takes months or years to build up speed. The Deep Space One probe, the first mission to use ion propulsion as its primary engine, took over a year to change its velocity by about 4 kilometers per second. For a human mission to Mars, that kind of slow acceleration would be unacceptable. Crew members cannot wait years to reach the planet, and ion thrusters also require a lot of electrical power. The more power you feed them, the more thrust they produce, up to a limit. For small robotic probes, solar panels are enough to supply that power, but for larger spacecraft carrying heavy payloads, you need much more power. That means either huge arrays of solar panels, which add mass and drag, or a dedicated nuclear reactor. Nuclear electric propulsion, where a fission reactor provides hundreds of kilowatts or even megawatts of electricity, could push the thrust of ion engines into a useful range. The reactor would power a set of large ion thrusters, giving the spacecraft a continuous but still gentle push. Over the course of a mission, the total velocity change could be enormous, allowing a spacecraft to travel to the outer planets or even to the Oort cloud. But the reactor itself is heavy, and the need for radiators to dump waste heat adds even more mass. The development of a space-rated fission reactor that is safe, reliable, and powerful has been a goal for decades, but no such reactor has ever flown beyond testing in low Earth orbit. Programs like NASA Kilopower project have demonstrated small reactors that could provide 10 kilowatts, but scaling up to a megawatt remains a huge engineering challenge. So electric propulsion offers the promise of extremely efficient travel, but only at the cost of patience and power. It is ideal for cargo missions or robotic scouting where time is not critical. For human crews, the slow acceleration would subject them to long periods in microgravity and expose them to accumulated radiation. The solution may be a hybrid approach, using fast chemical or nuclear thermal propulsion to get crews to their destination quickly, while sending heavy supplies and equipment ahead on slower ion-driven cargo ships. That way, the cargo arrives months later, after the crew has already started their return journey. Electric propulsion is not a universal answer, but it is a vital tool for the logistics of a spacefaring civilization. It gets us out of the rocket equations trap for certain payloads, yet it pulls us into a new constraint, the need for abundant, reliable, and space-rated electrical power. And that power problem leads directly to the next bottleneck that stands between us and the stars. Power is the invisible backbone of every space mission, and in deep space it becomes a crisis. Near Earth, solar panels work beautifully because sunlight is abundant. Each square meter receives about 1,300 watts of energy, enough to run instruments, communications, and life support with generous margins. But as a spacecraft travels further from the Sun, that number drops with the inverse square of distance. At Mars, sunlight is only half as intense as at Earth. At Jupiter, it falls to just 4%, at Saturn to about 1%, and beyond Neptune, the Sun is barely brighter than the brightest stars in our sky. Solar panels become useless long before a spacecraft reaches the outer planets. You could make them enormous, but size adds mass, and mass is the enemy of every rocket equation calculation. At some point, the panels themselves weigh more than the power they can produce, so engineers have turned to a different kind of energy source, one that does not depend on sunlight at all. The workhorse of deep space power for the last 5 decades has been the radioisotope thermoelectric generator, or RTG. An RTG uses the natural heat released by the decay of a radioactive isotope, usually plutonium-238, to generate electricity. There are no moving parts, no combustion, just a block of plutonium that stays warm for decades. Thermocouples convert that heat into a steady electrical current. Voyager 1 and 2, launched in 1977, still operate on their RTGs today, over 45 years later, because the plutonium half-life is nearly 90 years. They have flown past Jupiter, Saturn, Uranus, and Neptune, and one of them is now in interstellar space, still sending back a faint signal. The RTG is a proven, reliable, and remarkably simple technology. But it has a critical bottleneck. We do not have enough plutonium-238. For decades, the United States produced it at the Savannah River site as a byproduct of nuclear weapons production. When that program ended, the supply dried up. The remaining stockpile has been carefully rationed for flagship missions like the Mars Curiosity and Perseverance rovers, and for the upcoming Dragonfly mission to Titan. Each RTG requires several kilograms of plutonium, and the total available is measured in tens of kilograms, not hundreds. NASA and the Department of Energy have restarted limited production at Oak Ridge National Laboratory, but the output is slow and expensive. It costs billions of dollars to build the facilities and process the material, and even with the new production, the supply will barely meet the needs of one major mission per decade. The scarcity of plutonium-238 is a direct constraint on how many outer planet probes we can launch. For a human mission to Mars or beyond, the power requirements skyrocket. A rover like Curiosity needs about 100 watts. A crew habitat with life support, water recycling, air purification, and scientific equipment would need tens of kilowatts. An electric propulsion system for a cargo ship would need hundreds of kilowatts or even megawatts. RTGs cannot scale to those levels because they would require enormous quantities of plutonium, far beyond what we can produce, and the heat dissipation would become a nightmare. Each RTG generates waste heat that must be radiates away, and in a vacuum, heat only leaves by radiation. A multi-kilowatt RTG would glow red-hot and require massive radiator panels, adding more weight. So for human missions, the next step is fission nuclear reactors. A fission reactor splits atoms of uranium to generate heat, which is then converted to electricity. Unlike RTGs, fission reactors can be turned off and on, and they can produce power at any scale from a few kilowatts to megawatts. The key challenge is packaging a safe, lightweight, and reliable reactor that can survive launch and operate autonomously for years. NASA has been working on the Kilopower project, a small fission reactor designed specifically for space. Kilopower uses a solid uranium-235 core, surrounded by a heat pipe system that transfers thermal energy to Stirling engines, which convert heat into electricity with high efficiency. The first prototype, called Krusty, was tested successfully in 2018. It produced about 1 kilowatt of electricity and ran for over 28 hours, including simulated failure scenarios. The design is simple enough to be reliable, and it uses highly enriched uranium, which is more abundant than plutonium-238. The next step is to scale Kilopower up to 10 kilowatts and eventually to 100 kilowatts or more. But even Kilopower has limitations. It still needs radiators to dump waste heat, and the Stirling engines have moving parts that could wear out over a long mission. Alternative designs using thermoelectric converters or Brayton cycle turbines may offer better efficiency, and there is the perennial issue of safety. Launching a fission reactor means carrying a miniature nuclear power plant into orbit. Any accident during launch could spread radioactive material, and international treaties and public perception have made such launches rare. The only fission reactor ever launched by the United States was SNAP-10A in 1965, which operated for 43 days before a failure. The Soviet Union launched dozens of smaller reactors on their radar ocean reconnaissance satellites, but several of those malfunctioned and scattered debris across the Northern Hemisphere, creating a lasting public relations disaster. The lessons from those incidents have shaped a cautious approach. Modern space fission reactors are designed with multiple safety barriers and are kept in a subcritical state until they reach a safe orbit, so even a launch failure would not cause a chain reaction. But that adds complexity and cost. The technical challenges of heat dissipation in a vacuum are also severe. A reactor core operates at high temperature, and the waste heat must be rejected into space through radiators. The colder the radiators, the more efficient the conversion, but the larger they become. For a multi-megawatt reactor, the radiator array could be the size of a football field. And in deep space, those radiators are vulnerable to micrometeoroid impacts. So the power bottleneck is not just about generating electricity. It is about managing heat, minimizing mass, and ensuring decades of reliable operation without maintenance. The Kilopower program and its successors are promising, but they are still years away from flight qualification. Right now, every deep space mission must choose between the limited power of solar panels near the inner planets and the scarce, expensive, and low power output of RTGs for the outer planets. The gap between what we have and what we need for human exploration is enormous. Until we can deploy safe, high-power fission reactors in space, the outer solar system remains a dark place, and our dreams of mining the asteroids or building colonies on the moons of Jupiter and Saturn will stay just out of reach. The energy challenge is a quiet bottleneck, but it is one that will limit everything we can do beyond Earth until we solve it. Storing that power for sudden surges is an entirely different battle. Even the most powerful fission reactor in space cannot smooth out the spikes that a spacecraft demands in an instant. When an ion thruster fires at full throttle, when life support systems kick on to scrub carbon dioxide or heat a freezing habitat, or when a robotic arm draws current to weld a structure, the power draw can double or triple in seconds. A reactor or solar array may be rated for a steady baseline, but it cannot respond that fast. That is where energy storage steps in and the challenge begins. Batteries, fuel cells, and supercapacitors must bridge the gap between what the power source can deliver continuously and what the mission needs in short, intense bursts. The environment in space makes this far harder than on Earth. Temperatures can swing from 150 degrees Celsius in direct sunlight to -200 in the shadow of a planet or an asteroid. Radiation, especially in the Van Allen belts or beyond low Earth orbit, degrades the chemical bonds inside conventional lithium-ion batteries, causing them to lose capacity over months. Electrolytes freeze or boil, electrodes swell and crack, and charge cycles become unreliable. Storing enough energy from one peak to the next also demands high density. For a crewed mission, a sudden propulsion burn might require megawatts for minutes. A battery bank that could deliver that surge would be enormous and heavy, eating into the mass budget for everything else. Supercapacitors can handle bursts well but store very little total energy, so they are best paired with other systems. Fuel cells combine hydrogen and oxygen to produce electricity and water, which is a valuable resource, but they require cryogenic storage of the reactants, which boils off over time. Regenerative fuel cells reverse the process using solar or nuclear power to split water back into hydrogen and oxygen, creating a closed loop, but the efficiency is low and the components are heavy and complex. The most promising candidates for deep space are solid-state batteries. They replace the liquid electrolyte with a solid ceramic or polymer, making them far more resistant to temperature extremes and radiation. They can operate at higher voltages and pack more energy per kilogram than today's lithium-ion cells. Research at institutions like NAS, a Glenn Research Center, has shown solid-state prototypes surviving hundreds of cycles in vacuum and under intense gamma radiation. But they are still in early development with limited production capacity and high cost. Another avenue is flow batteries, which store energy in liquid electrolytes held in separate tanks. They can be scaled by simply making the tanks larger, and they degrade far less over time. But the pumps and membranes needed to circulate the liquid add moving parts that can fail in zero gravity. Regenerative fuel cells may ultimately dominate for long-duration missions because they double as a water supply, but they need a reliable source of power to recharge and a system to manage the hydrogen and oxygen across years of operation. In the bottleneck of energy storage, the trade-offs are stark. Do you carry heavy batteries that may degrade before arrival? Do you accept the boil-off and risk of cryogenic fuel cell reactants? Or do you invest in unproven solid-state technology that could revolutionize mass efficiency? Every mission architect must weigh these choices against the harsh realities of space. The answer will shape not just how we power a single spacecraft, but the entire infrastructure of a spacefaring civilization where energy must be stored, released, and reused across decades of operation and across distances that stretch far beyond Earth. Radiation is an invisible wall that stops every deep space mission before it truly begins. Unlike the rocket equation or propulsion limits, this barrier cannot be solved by burning more fuel or building a bigger engine. It is a fundamental hazard of the environment beyond Earth's protective magnetic field and atmosphere. Out there, two distinct sources of radiation threaten any living tissue or electronic component. The first is galactic cosmic rays, or GCR, a constant drizzle of high-energy particles that come from outside our solar system, accelerated by supernova explosions and other violent events across the galaxy. These particles travel at nearly the speed of light and punch through matter like bullets through paper. The second source is solar particle events, or SPE, which are bursts of energetic protons flung out by the sun during flares or coronal mass ejections. SPEs can be intense but brief, while GCRs are a steady, relentless background. Both are dangerous, but in different ways. GCRs cause cumulative damage over time, breaking DNA strands and increasing the risk of health challenges later in life. SPs can deliver a lethal dose in hours if a crew is caught outside a shielded shelter. The problem is that shielding against this radiation is not straightforward. The traditional approach, passive shielding, works by placing mass between the crew and the radiation source. On Earth, that mass is the atmosphere and the planet itself. In space, you have to bring the mass with you. Aluminum walls, water tanks, polyethylene panels, all of these materials absorb or slow down particles. But here is the catch. To reduce GCR exposure to safe levels, you need about 5 meters of water or its equivalent in shielding mass. That is roughly 5 tons per square meter of hull area. For a crew habitat with a surface area of hundreds of square meters, the shielding mass would dwarf the rest of the spacecraft. The rocket equation punishes that weight mercilessly. You would need enormous amounts of fuel just to lift the protection, and even then, the protective layers themselves create a secondary problem. When high-energy particles hit a thick shield, they can break apart into secondary particles like neutrons and gamma rays that are often more damaging than the originals. This is called the showering effect. A thick aluminum wall can actually increase the radiation dose behind it for certain particle energies, so passive shielding is a losing game for deep space missions. Engineers have known this for decades, and that is why they have turned to a different approach. Active shielding uses magnetic fields or electrostatic charges to deflect charged particles before they reach the habitat. The concept is inspired by Earth's own magnetic field, which diverts most cosmic rays and solar particles. A spacecraft could generate a similar field around itself using powerful superconducting magnets or charged plates. The advantage is that the mass of the magnetic coils and power supply can be much less than the equivalent passive shielding. The challenge is that the field must be strong enough to bend the path of particles moving at near light speed. For galactic cosmic rays, you need a magnetic field on the order of several Teslas. comparable to an MRI machine, but spanning a volume large enough to enclose a crew module. That requires superconducting magnets that operate at cryogenic temperatures, adding complexity and power demands. Electrostatic screens are another option, where a charged outer shell repels positively charged particles like protons. But electrons and neutral particles still pass through, and the voltage required to stop the most energetic particles is in the millions of volts, which creates risks of arcing and electrical breakdown in the vacuum of space. Every active shielding concept faces the same fundamental trade-off. The more protection you want, the more energy and mass you need. The most promising current research involves combining a small magnetic field with a lightweight shell of hydrogen-rich materials like polyethylene or water that can capture secondary neutrons without adding too much weight. The idea is to use a modest magnetic field to deflect the majority of particles, while a thin passive layer absorbs the remainder. This hybrid approach could cut the total shielding mass by a factor of 10 compared to passive alone. But it is still in the laboratory phase. No full-scale active shield has ever been tested in space. The technology for reliable, lightweight superconducting magnets that can operate for years without maintenance does not exist yet. The power needed to maintain the field, even with superconducting coils, must come from a reactor or large solar arrays, which brings us back to the power bottleneck. And there is another subtle point. The magnetic field itself interacts with the charged particle environment, potentially creating trapped radiation belts around the spacecraft similar to the Van Allen belts around Earth. Those trapped particles could increase the dose to the hull and to any crew who need to perform spacewalks, so the solution is not as simple as turning on a big magnet. It requires careful modeling of particle trajectories and continuous adjustment of the field. The bottom line is that radiation shielding is one of the hardest unsolved engineering problems for human deep space exploration. Without a breakthrough, crewed missions to Mars or beyond would be limited to short durations, perhaps a few months, before cumulative radiation exposure exceeds established safety limits. For a round trip to Mars lasting 2 to 3 years, the total dose from GCRs alone would approach or exceed career limits for astronauts according to current guidelines. That means every mission beyond low Earth orbit must either accept higher risk, develop shielding that works, or find ways to travel much faster to reduce exposure time. And even a faster transit does not eliminate the problem because the shielding itself still adds mass that slows the spacecraft. The radiation wall is not visible, but it is as real as any concrete barrier. It forces mission planners to choose between crew safety and mission duration, and neither choice is easy. The search for a practical, lightweight shielding solution continues in laboratories around the world, and it may turn out that the best shield is not a solid wall at all, but a combination of fields, materials, and clever orbital timing that together hold the invisible wall at bay. A separate wall, just as unforgiving, surrounds the problem of keeping a crew alive for years without resupply. On the International Space Station, astronauts are never more than a few months away from a cargo ship bringing fresh water, food, and oxygen. The station's life support systems recycle some of the air and water, but they are far from perfect. About 40% of the water from urine and humidity is recovered, and the rest is lost because the equipment cannot capture every molecule. The carbon dioxide removal system uses a chemical called lithium hydroxide, which must be replaced regularly with new canisters shipped from Earth. Those canisters add mass, and every extra kilogram is a burden on the launch manifest. For a mission to Mars or beyond, that kind of reliance on resupply is impossible. The supply line would stretch across hundreds of millions of kilometers, and a cargo ship would take months to arrive. The crew would need to recycle everything: air, water, food, and waste with near-perfect efficiency. Losing even a few % of the water each cycle would drain the tanks before the mission ended. The engineering challenge is to close every loop so tightly that nothing escapes. The ISS systems are a starting point, but they are not designed for long-duration autonomy. The water recovery system has multiple filters and distillation steps, but the equipment is bulky, power-hungry, and prone to clogging. The oxygen generation system splits water into hydrogen and oxygen using electrolysis, but the hydrogen is usually vented overboard because there is no good use for it. That vented hydrogen represents lost water molecules. On a deep space mission, you would need to capture that hydrogen and combine it with carbon dioxide to make more water, a process called the Sabatier reaction. That reaction is well understood on Earth, but building a compact, reliable reactor that works in microgravity and can operate for years without maintenance is a separate challenge. Every component must have backups because a single failure in the recycling chain could lead to a runaway loss of a critical resource, and the entire system must be able to self-monitor and repair because there is no technician on the ground to fix a leaking valve. Beyond air and water, there is the hardest loop of all, food. On the ISS, astronauts eat pre-packaged meals that are delivered every few months. Those meals are grown on Earth, processed, and shipped. They provide all the necessary nutrients, but they are heavy, they take up storage space, and they have a limited shelf life. For a multi-year Mars mission, carrying enough food for the entire journey would add thousands of kilograms of mass. The only practical solution is to grow food in space, using plants to convert carbon dioxide, water, and light into edible biomass. This is called bioregenerative life support, and it is a field that researchers have studied for decades. The idea is to create a closed ecosystem where plants produce oxygen, consume carbon dioxide, and provide food, while microbes break down waste and recycle nutrients back into the soil. It sounds elegant, but the reality is messy. Plants need light, water, nutrients, and a controlled atmosphere. They are sensitive to pests, diseases, and fluctuations in temperature. They grow slowly, and the yield per square meter is low. A crew of 4 would need a greenhouse area the size of a tennis court just to supply a fraction of their diet. And that greenhouse would require a lot of energy for lighting, pumping water, and maintaining air circulation. Algae offer a different path. They grow much faster than plants and can be cultivated in tanks of water with minimal light and nutrients. Certain strains of algae are rich in protein, fats, and carbohydrates, and they can be harvested continuously. The oxygen they produce could supplement the electrolysis system. But algae have their own problems. The tanks need to be stirred or mixed to prevent clumping, and the harvested biomass must be processed into edible forms. The taste and texture of algae-based food is not appealing to most people, and long-term consumption may cause digestive issues. Engineering a reliable, fail-safe algae bioreactor that can operate for years without clogging, contamination, or power interruptions is a daunting task. Even minor fluctuations in pH or temperature can crash the culture. Another approach uses microbial fuel cells to break down solid waste into methane and other useful compounds. The methane could be burned for heating or used as propellant. The microbes themselves could be engineered to produce vitamins or specific amino acids that are missing from the plant-based diet. But these systems are still experimental. They require careful control of microbial communities, and they produce a complex soup of chemicals that must be separated and purified. Every extra step in the recycling chain adds points of failure. The engineering hurdle is not just about efficiency, it is about reliability and autonomy. A closed-loop life support system must run for thousands of hours without human intervention. It must detect and correct faults, reboot after power outages, and adapt to changing crew demands. No such system has ever been built and tested for the full duration of a Mars mission. The nearest analog is the Mi-Li SSA project, a European Space Agency effort that aims to develop a closed-loop life support system using a combination of bioreactors and physico-chemical processes. They have demonstrated small-scale prototypes that recycle air, water, and some nutrients, but the entire system is far from flight-ready. The consensus among engineers is that a fully closed-loop system for a crew of 4 is at least a decade away from operational deployment. Until that day comes, every deep space mission will rely on a mix of recycling, stored supplies, and careful budgeting of resources. The crew will live with the constant awareness that a single malfunction could turn the habitat into a slowly depleting vault. The walls of the loop are not just physical, they are psychological. The ability to sustain life far from Earth depends on our ability to master the small, invisible cycles that we take for granted on this planet. And that mastery is still incomplete, a quiet bottleneck that holds back every dream of a permanent presence beyond low Earth orbit. Microgravity slowly dismantles the human body, and the only known solution to stop that destruction is to spin the spacecraft. In the weightlessness of orbit, bones lose density at about 1% per month, muscles atrophy, fluids shift upward into the head, and the spine expands. Vision changes, balance degrades, and the immune system weakens. Astronauts on the International Space Station spend hours each day exercising to slow the damage, but no amount of resistance training can fully prevent the long-term consequences. After a year in microgravity, recovery on Earth takes many months, and some changes may be permanent. For a multi-year mission to Mars or beyond, the crew would face levels of deterioration that could leave them unable to walk on a planet's surface, let alone perform complex tasks. The answer is not better exercise, it is a centrifuge. The idea is simple. By rotating a spacecraft or a section of it, you create a centrifugal force that mimics gravity. The outer wall of the rotating structure becomes the floor, and the crew inside feels a pull outward, as if they were standing on a planet's surface. The faster the rotation or the longer the radius, the stronger the apparent gravity. But engineering a rotating habitat in space is far from trivial. The first challenge is structural. A rotating spacecraft must be balanced to within a tiny margin of error. Any asymmetry in mass distribution creates wobbles that can tear the structure apart. The rotation must be stable without precession or nutation, and the entire system must withstand the bending moments and stresses that come from spinning a large object in a vacuum. The second challenge is human. When you rotate your inner ear, the vestibular system detects the rotation. For a person standing inside a rotating habitat, the Coriolis effect becomes noticeable. If you move your head quickly, the fluid in your ear canals experiences a different flow, leading to dizziness, disorientation, and nausea. The same effect causes objects dropped from a height to appear to curve. The faster the rotation, the stronger these Coriolis forces. To keep them tolerable, the rotation rate must be low, typically below 2 revolutions per minute. At that speed, the radius of the habitat must be large to still produce useful gravity. A simple formula governs this. The radius needed equals the acceleration of gravity divided by the square of the rotation rate. For Earth normal gravity of 9.8 meters per second squared and a rotation rate of 1 revolution per minute, the required radius is about 890 meters. That is nearly a kilometer across. A structure that large is far beyond anything we have ever built in space. Even at 2 revolutions per minute, the radius drops to about 220 meters. That is still enormous for a single spacecraft. The classic design that addresses this is the Stanford Torus, a concept from a 1975 NASA study. It is a giant ring shaped like a donut with a diameter of about 1.8 kilometers. The torus rotates to provide Earth normal gravity. Inside, the ring is wide enough to hold a small community with homes, parks, and agriculture. The central hub remains stationary for docking, and spokes connect the hub to the ring. The torus is a beautiful vision, but its construction would require massive orbital infrastructure, mining asteroids for materials, assembling the ring in space, and spinning it up carefully to avoid disaster. A more immediate concept is the spinning Starship. Elon Musk has proposed that when Starship reaches Mars, it could be parked in a high orbit and spun to provide gravity during the return trip. Starship's hull is about 9 meters in diameter and 50 meters long. If you rotate it end over end, the crew at the opposite ends would experience a fraction of Earth gravity. But the radius is only 25 meters from the center to the nose. To get Earth normal gravity at that radius, you would need to spin at about 6 revolutions per minute, which is far beyond the comfort limits for most people. The Coriolis forces would be strong enough to cause severe motion sickness and disorientation. So a spinning Starship could only provide partial gravity, perhaps a third of Earth's, at a moderate rotation rate. That might be enough to prevent the worst effects of microgravity, but it remains an open question. The third challenge is mechanical. A rotating spacecraft must have a non-rotating section for docking and communications, because antennas and solar panels need to point steadily at Earth and the Sun. That means a slip ring or a rotary joint to transfer power and data between the two sections. These joints are complex, prone to wear, and expensive to build for the long durations of a deep space mission. Every moving part is a potential failure point, and the entire rotating structure must be balanced not just once, but continuously, as fuel is consumed and cargo is moved. Small adjustments would require reaction wheels or thrusters to maintain the spin axis. The engineering complexity grows quickly with size, so the trade-off is painful. You can build a small rotating section that spins fast and makes your crew sick. You can build a large rotating ring that is comfortable but requires decades of orbital construction. Or you can accept the health risks of microgravity for a shorter trip, hoping that exercise and medication can keep the crew functional. No one has yet found a middle ground that is both practical and safe. The dream of artificial gravity remains trapped between the limits of human physiology and the limits of orbital engineering. Every mission architecture must decide how much gravity, how much radius, and how much risk it can afford. And that decision shapes everything else, from the size of the habitat to the duration of the journey, to the very design of the spaceship itself. A spacecraft can only carry so much fuel and water. No matter how efficient the engines or how comfortable the artificial gravity, every mission beyond Earth eventually runs into the same hard limit, the mass you left on the launch pad. The only way to break that limit is to stop carrying everything from home and start making what you need when you get there. That idea is called In-Situ Resource Utilization, or ISRU, and it is the single most important technology for turning fleeting visits into permanent outposts. Consider the Moon. Its surface is covered in a fine gray powder called regolith, which is rich in oxygen. In fact, nearly half the mass of lunar soil is oxygen bound up in minerals like ilmenite and pyroxene. If you can heat that regolith to extreme temperatures, the oxygen is released as a gas. A small processing plant on the lunar surface could produce enough oxygen to supply a habitat and even to fill propellant tanks for return trips. The same regolith contains metals like aluminum and silicon that could be used for construction or for manufacturing solar panels. But the challenge is not theoretical chemistry. It is building a machine that can scoop up dusty, abrasive soil, heat it to over 900 degrees Celsius in a vacuum, separate the gases, cool them, store them, and do it all without human supervision for years. The dust itself is a nightmare. Lunar regolith is sharp, electrostatically charged, and sticks to everything. It clogs filters, wears down moving parts, and can cause seals to fail. Every robotic arm, every valve, and every crusher must be designed to survive in that environment. Mars adds another layer of complexity and opportunity. The Martian atmosphere is 95% carbon dioxide. That gas can be captured and processed through a reaction with hydrogen to produce methane and water. Methane is the fuel that many advanced rocket engines, including SpaceX's Raptor, are designed to burn. Water can be split into hydrogen and oxygen, giving you both breathing gas and more propellant. The Sabatier reaction, as it is called, is well understood on Earth, but doing it on Mars requires a chemical plant that can operate in freezing temperatures, low atmospheric pressure, and with unpredictable dust storms that block sunlight for weeks. The plant must compress the thin Martian air, filter out dust, and maintain precise temperatures and pressures. Every moving part must be hardened against the abrasive dust. The entire system must be able to start up and shut down autonomously because there is no one on the ground to flip a switch. The water itself is not easy to reach either. On both the Moon and Mars, water exists mostly as ice buried beneath the surface. On the Moon, it is concentrated in permanently shadowed craters at the poles, where temperatures never rise above -200 degrees Celsius. Drilling into that ice, melting it, and pumping the liquid water requires equipment that can survive extreme cold and then operate in a vacuum. On Mars, water ice lies just below the surface in many mid-latitude regions, but the soil is laced with perchlorates, toxic salts that must be removed before the water is safe for drinking or for splitting into hydrogen. The processing chain is long: drill, excavate, heat, distill, purify, and then feed into the chemical reactor. The power required for all of this is enormous. A single oxygen production plant on the Moon might need tens of kilowatts continuously, and a full-scale methane fuel refinery on Mars could require hundreds of kilowatts. That power must come from solar panels, nuclear reactors, or both. Solar panels on Mars are vulnerable to dust covering them, which cuts output dramatically. Nuclear reactors, as we discussed earlier, bring their own weight and safety concerns, and every piece of the ISRU system must be landed on the surface, which means it must survive the violent deceleration of entry, descent, and landing. A single broken pipe or a jammed valve could halt production entirely. The stakes are high. Without ISRU, returning from Mars would require bringing all the propellant for the ascent vehicle from Earth, adding tens of tons to the launch mass. With ISRU, you only need to send the processing plant, which is far lighter. The difference is the difference between a possible mission and an impossible one. That is why every serious plan for a human Mars mission, from NASA, a design reference architecture to SpaceX's Starship architecture, depends on ISRU. The first cargo landers sent ahead of the crew would carry empty propellant tanks and the machinery to fill them. The crew would arrive only after the tanks are full, but the engineering hurdles are not merely mechanical. The control software that runs an ISRU plant must handle thousands of sensors and actuators, detect faults, and execute recovery procedures without human guidance. It must manage thermal cycles, pressure fluctuations, and resource inventories. It must decide when to vent excess gases, when to store products, and when to shut down if something goes wrong. Developing that level of autonomy is a massive software challenge, far beyond what current space missions require. The promise of ISRU is that it transforms the harshness of alien worlds into an advantage. Instead of being a barren wasteland, the Moon and Mars become vast warehouses of raw materials. The regolith is not just dirt, it is ore. The atmosphere is not just thin and deadly, it is a chemical feedstock. The ice is not just frozen water, it is the key to returning home. Every gram of propellant we manufacture on another world is a gram we did not need to lift from Earth. That is the lever that breaks the rocket equation, not by building a bigger rocket, but by not needing to carry everything with you. It is a quiet revolution, one that happens not in the roar of engines but in the silent, automated hum of chemical plants on distant worlds, slowly turning rock and air into the fuel for the next great leap. Microgravity offers a factory floor unlike anything on Earth. In the absence of weight, materials behave differently. Sedimentation stops, convection currents disappear. Fluids and melted metals can form into shapes that gravity would pull apart. That opens the door to manufacturing products that are impossible to make on our planet. Imagine drawing a fiber optic cable that is perfectly uniform for kilometers because no sagging or turbulence distorts the molten glass. Imagine growing a crystal for electronics where every atom locks into place without a single dislocation. In space, these perfect structures become routine. The same applies to advanced alloys. On Earth, different metals tend to separate as they cool, heavier elements sinking, lighter ones floating. In microgravity, that separation never happens. You can blend metals that would otherwise be immiscible, creating alloys with unprecedented strength, conductivity, or heat resistance. For semiconductors, the ability to grow larger and more perfect crystals could boost computing power dramatically. For medicine, protein crystals that are nearly flawless can reveal molecular structures that help design new drugs. The potential value of these space-made materials is enormous, enough to pay for entire missions if a market can be built. But the bottleneck is not the science. It is the logistics. Every kilogram of raw material must be launched from Earth at a cost that, even with reusable rockets, remains high. You have to lift the feedstock, the furnaces, the shaping tools, and the power supply. That weight cuts directly into the rocket equation, and the finished product must be brought back down, which costs nearly as much as sending it up. So the economics only work for extremely high-value items, like certain pharmaceuticals or specialty optical fibers. The real breakthrough will come when we stop shipping raw materials from Earth altogether. That is where mining and processing on the Moon or asteroids changes the equation. If you can extract metals, silicon, and carbon from local rock, then the launch cost no longer applies. You are only lifting the manufacturing equipment once. After that, the factory feeds itself from the ground beneath it. That vision is behind concepts like the robotic 3D printer that uses lunar regolith as feedstock. Instead of making propellant, the same soil can be melted and extruded into beams, panels, or even entire habitats. Layer by layer, a printer could build a landing pad, a shelter, or a radiation shield using nothing but dirt and sunlight. That would slash the mass that needs to be delivered from Earth. But the challenge is making those printers reliable in a vacuum, with abrasive dust and extreme temperature swings. Every nozzle must resist clogging, every motor must survive thousands of hours without maintenance, and quality control in zero gravity is not trivial. Without gravity to settle a layer, printed structures can warp or delaminate. Engineers must develop new ways to bond layers, perhaps using microwave sintering or laser melting that fuses the regolith into solid stone. The first 3D printed structures on the Moon will likely be simple blocks, tested for strength and durability. Over time, the technology will improve, producing more complex shapes and even integrated electronics. The ultimate goal is a self-replicating factory that can build almost anything needed for a permanent outpost, from spare parts to solar panels, using only local materials. That future is still distant, but each step forward reduces our dependence on the thin thread of Earth resupply. And when that thread is finally cut, the true spacefaring civilization begins. The raw materials waiting on the Moon and asteroids are only half the promise. Even with unlimited regolith, water, and metals, every structure we build in space still demands a material that can survive the journey and the environment. The spacecraft itself, its hull, its trusses, its shielding, its solar panel supports, must endure extremes that tear ordinary materials apart. In low Earth orbit, a satellite experiences temperature swings of over 200 degrees Celsius as it passes from sunlight into shadow. On the lunar surface, the day-to-night swing is even more severe, nearly 300 degrees. That thermal cycling expands and contracts metals, causing fatigue and microcracks that grow over time. Micrometeoroid impacts, tiny grains of sand traveling at many kilometers per second, punch through ordinary aluminum like bullets through paper, and radiation slowly embrittles polymers and degrades composites. The materials we have today, aluminum alloys, titanium, and standard carbon fiber composites, are the best we can produce at scale, but they are not good enough for the long-duration, high-reliability structures we need for a permanent space presence. Engineers have known for decades what the ideal materials would look like. They would be extremely lightweight because every kilogram of structure costs kilograms of propellant to lift. They would have high strength to resist the forces of launch and landing. They would withstand thousands of thermal cycles without cracking. They would absorb micrometeoroid impacts without penetrating. They would block radiation without adding mass, and they would be self-healing, able to repair small cracks or punctures automatically, because you cannot send a repair crew to patch a leak in the middle of a deep space voyage. Carbon nanotubes have long been the poster child for this dream. A single nanotube is 100 times stronger than steel at 1/6 the weight. A cable woven from nanotubes could theoretically support a space elevator stretching from Earth to geostationary orbit. But producing nanotubes in bulk with consistent quality and at a reasonable cost has proven enormously difficult. The best methods still produce material with defects, impurities, and limited length. A nanotube fiber that is strong in the lab often loses half its strength when scaled up to a continuous thread. The production rate is measured in grams per day, not kilograms per hour, and the cost remains astronomical. Composites are further along. Layered sheets of carbon fiber embedded in a resin matrix are already used in aircraft, rockets, and satellites. They offer excellent strength-to-weight ratios and can be tailored to specific loads. But in the vacuum of space, the resin outgasses, releasing volatile compounds that can fog optics and contaminate sensitive instruments. Over years of exposure to ultraviolet light and atomic oxygen, the resin degrades, becoming brittle and prone to cracking. Newer composites use ceramic or metal matrices that are more stable, but they are heavier and harder to shape. Self-healing metals represent another frontier. Researchers have developed alloys that contain tiny capsules of liquid metal or a healing agent. When a crack propagates through the material, the capsules burst, releasing the agent which fills the fracture and solidifies. In laboratory tests, these alloys have restored up to 90% of their original strength after being damaged. But the healing process is slow. It requires the right temperature conditions, and the capsules themselves reduce the base strength of the material. Scaling up production of these alloys to the tonnage needed for a large spacecraft is a challenge that has not been solved. The fundamental bottleneck is not scientific understanding. It is manufacturing. We know how to make small quantities of extraordinary materials in controlled conditions. We do not know how to make them in the vast quantities that a spacefaring civilization would need at a price that makes them practical. The gap between a lab sample and a flight-ready structure is enormous. It involves developing industrial processes that can run continuously with consistent quality control, using raw materials that are readily available. It involves testing every batch for defects, certifying the material for decades of service, and integrating it into designs that can take full advantage of its properties. And all of that must happen before a single rivet is ever launched. The spacecraft of the future, the ones that will carry us to Mars, to the asteroid belt, and to the moons of the outer planets, will be built from materials that barely exist today. They will be lighter, stronger, and more resilient than anything we have now. But first, we must master the art of making them not just in a laboratory, but in a factory that can supply a fleet. That is a bottleneck that will take years of steady, incremental engineering to break, and it is one of the quietest, most overlooked barriers between us and the stars. Heat is a silent enemy in the vacuum of space. On Earth, when a machine gets hot, you can cool it with a fan, a water jacket, or simply let the surrounding air carry the heat away. Convection and conduction are fast and efficient, but in the emptiness beyond our atmosphere, there is no air to carry heat and no water to absorb it. The only way to shed excess thermal energy is through radiation, the slow, invisible emission of infrared light. That turns every spacecraft into a carefully balanced thermal problem. Every electronic component, every thruster, every life support machine generates waste heat. If that heat is not removed, it builds up until temperatures climb into dangerous territory. Electronics fail, seals melt, and habitats become uninhabitable. Yet the radiator that must dump that heat is itself a heavy, bulky structure that adds mass and takes up space. Every square meter of radiator area only emits a few hundred watts at realistic operating temperatures. To remove tens of kilowatts, you need tens of square meters of radiating surface. And those radiators must face away from the sun because if sunlight hits them, it adds heat instead of removing it. That means the spacecraft must constantly orient itself or use movable radiator panels that track the sun. The trade-off is brutal. You can run your equipment hot, which makes the radiators smaller but stresses the components, or you can run it cool, which makes the radiators huge and heavy. The optimum point depends on the mission. For a crewed habitat, the ideal internal temperature is around 20 degrees Celsius. At that temperature, a radiator emits only about 150 watts per square meter. To dump 10 kilowatts, you need over 60 square meters of radiator area, roughly the size of a small apartment. And those panels must be deployed after launch, adding complexity and points of failure. Advanced concepts try to push past these limits. One approach uses liquid metal loops, such as a mixture of sodium and potassium, to transport heat from the source to the radiators. Liquid metals can carry far more heat than water or ammonia, and they remain liquid across a wide temperature range. The loop is pumped through pipes that snake across the radiator panels, spreading the heat evenly. But the pumps must run continuously, and any leak in the loop would be catastrophic because the metal would freeze or react with the spacecraft. Another idea is deployable radiators that unfold like an accordion or a fan once in orbit. These can be packaged tightly during launch and then unfurled to many times their stowed size. The International Space Station uses this approach with large radiator wings that hinge out. But those radiators are designed for low Earth orbit, where they also get a little help from the thin atmosphere. In deep space, the radiators must be even larger, and the deployment mechanisms must be absolutely reliable. A stuck panel could mean a rapid rise in temperature and the end of the mission. A more exotic solution is thermophotovoltaic cooling. Instead of just radiating heat away, these systems convert some of the infrared energy into electricity. A hot surface emits photons, and a photovoltaic cell tuned to those wavelengths captures a fraction of them, generating power while also cooling the source. The efficiency is low, typically around 10 to 20%. But every watt of electricity you recover is a watt of heat you do not need to dump. That can shrink the radiator size and provide extra power for the spacecraft. The challenge is that the photovoltaic cells must be specially designed to match the emission spectrum of the hot surface, and they themselves get hot and must be cooled. The system becomes a layered stack of materials, each with its own thermal and electrical properties. All of these thermal management technologies share a common bottleneck: mass. Every kilogram of radiator, every meter of pipe, every pump and valve must be lifted from Earth. And because heat rejection is a continuous process, not a one-time event, the radiator mass scales with the power the spacecraft uses. A more powerful reactor or a faster propulsion system means more waste heat and bigger radiators. The relationship is so tight that in many spacecraft designs, the radiators account for a significant fraction of the total dry mass. That is why engineers spend years optimizing every fin, every channel, every coating to squeeze out a few percentage points of efficiency. The goal is to make the radiators light enough that the rest of the spacecraft can actually do its job. And until we develop materials that can radiate more heat per square meter, or systems that can convert waste heat into useful energy, thermal management will remain a quiet but relentless bottleneck, a constant reminder that in the cold of space, the biggest challenge is not staying warm but staying cool. Distance does more than stretch travel time. It stretches the thread of communication until it snaps. When a spacecraft is near Earth, signals travel in less than a second, so engineers can steer every move, send commands, and watch the response in near real time. But as the vehicle pushes outward, that thread grows thinner and longer. At the Moon, the round-trip delay is about 2.5 seconds, annoying but manageable. At Mars, the delay ranges from 4 to 24 minutes, depending on planetary alignment. That means a simple question like, "Should I adjust the antenna?" would take nearly an hour to answer. By the time the reply arrives, the spacecraft has already moved, and the situation may have changed entirely. At Jupiter, the delay stretches to over an hour each way. At Saturn, more than 2 hours, and at Neptune, over 4 hours. Real-time control becomes impossible. You cannot joystick a rover on Mars. You cannot troubleshoot a sudden engine failure from Earth. The spacecraft is on its own. That is not a limitation we can fix with better antennas or faster radios. The speed of light is a universal constant, and it sets the absolute floor on how quickly information can travel. No amount of engineering can shrink the gap. The only solution is to give the spacecraft a mind of its own. It must be able to navigate, detect faults, diagnose problems, and make decisions without waiting for instructions from the ground. That means embedding artificial intelligence directly into the flight computer, not just as a helper, but as a full partner capable of running the entire mission autonomously for months or years. Today's space probes have a limited form of autonomy. They can execute pre-programmed sequences, detect certain errors, and switch to a safe mode, but they cannot adapt to unexpected situations or make complex scientific judgments. When the Mars rover Curiosity finds an interesting rock, it cannot decide on its own to take a closer look. It must wait for a team of scientists to analyze the images, debate the options, and upload a new command sequence. That process takes a full day. On a distant moon of Jupiter, where the communication delay is hours, that kind of back and forth would grind exploration to a halt. The rover might sit idle for days while Earth decides what to do next. The next generation of deep space probes needs a different kind of intelligence. They need to be able to recognize a novel geological feature, prioritize it against other objectives, and execute a series of observations without any human input. They need to be able to detect a malfunction in a thruster, diagnose the root cause, and reroute control to a backup system, all within seconds. That level of autonomy requires software that is far beyond what we have today. It requires machine learning models that can reason about the world, handle uncertainty, and learn from experience. It requires fault detection algorithms that can distinguish between a minor anomaly and a critical failure. And it requires a decision-making framework that can balance competing goals, science collection, power management, thermal limits, and communication windows. The challenge is not just writing the code, it is verifying that the code will work correctly in every conceivable situation, because there is no second chance. A single bug in the autonomy software could send $1 billion probe into a crater or cause it to burn up in an atmosphere. The testing and validation of autonomous AI for deep space is a bottleneck that is only beginning to be addressed. Researchers are developing techniques like formal verification, where mathematical proofs confirm that the software will never make a dangerous decision. They are building simulation environments that model thousands of failure scenarios to train the AI to respond correctly. But these methods are still slow and expensive, and they do not scale easily to complex, open-ended tasks like scientific discovery. The result is a tension between capability and trust. We could build a spacecraft that is highly autonomous, but we do not yet know how to guarantee that it will not make a catastrophic mistake. So we hold back, relying on more conservative programming that limits what the probe can do on its own. That cautious approach works for near-Earth missions, but it will not work for the outer solar system. Until we crack the autonomy bottleneck, every mission to Jupiter, Saturn, and beyond will be crippled by the long, silent gaps between commands, waiting for a message that takes hours to arrive. The spacecraft will be like a brilliant student forced to raise a hand for permission before every action, never able to act on its own insight. And the discoveries that wait at the edge of the solar system will stay just out of reach, not because we cannot get there, but because we cannot let go of the leash. The spacecraft must learn to think for itself, and that learning must happen on hardware that is decades behind what powers everyday life on Earth. A modern smartphone runs a processor with billions of transistors and can perform trillions of operations per second. The flight computer on the Mars rover Perseverance, by contrast, uses a radiation-hardened chip that delivers about the same performance as a mid-1990s laptop. That gap exists because the electronics that survive the harsh environment of space cannot simply be off-the-shelf components. Cosmic rays and solar particles constantly bombard the circuitry, flipping bits in memory and causing crashes. To withstand that, space-grade chips are built with larger transistors, redundant logic, and specialized shielding, all of which dramatically reduce speed and efficiency. The result is a severe constraint on how much artificial intelligence can run onboard. The most advanced terrestrial AI systems, like those that drive autonomous cars or play complex games, require multiple graphics processing units consuming hundreds of watts. A space-rated computer can only handle a tiny fraction of that load, so engineers must strip down the AI to its essentials, using simpler algorithms that can run on limited memory and clock cycles. For hazard detection during landing, for example, the computer must analyze images of the surface in real time to identify rocks, slopes, and craters. Perseverance uses a system called terrain relative navigation, which compares camera images to an onboard map. That works well for a known area, but it is not truly adaptive. A future mission to a completely unexplored location, like the subsurface ocean of Europa, would need a more flexible vision system that can recognize unknown hazards and adjust the landing site on the fly. That requires deep neural networks, which are far more demanding. The same challenge applies to planning under uncertainty. A rover on Mars might need to decide whether to climb a steep ridge to reach a scientifically interesting outcrop, or take a longer, safer path around it. That decision involves weighing the risk of a wheel getting stuck against the value of the data. Current rovers rely on ground controllers to make that call because the onboard computer cannot run the complex simulations needed to evaluate all the possibilities. For a probe orbiting Jupiter, where the communication delay is over an hour, that luxury disappears. The spacecraft must evaluate the trade-offs itself and choose an action without confirmation. That kind of planning under uncertainty is an active area of AI research on Earth, but it requires enormous computational resources. Health monitoring is another area where the gap shows. Today, spacecraft carry a list of predefined alarm thresholds. If a temperature exceeds a certain value, the computer triggers a safe mode and waits for instructions. But those thresholds are conservative, and many subtle failure modes go unnoticed until it is too late. A more intelligent system could learn the normal behavior of every sensor and detect anomalies early, potentially preventing a failure. It could even diagnose the root cause by correlating readings from different parts of the spacecraft. That level of monitoring demands continuous machine learning inference across hundreds of data streams, a task that far exceeds the capacity of current flight hardware. Researchers are pursuing several paths to close this gap. One is the development of specialized radiation-hardened chips designed specifically for AI workloads, such as field-programmable gate arrays or application-specific integrated circuits that can run neural networks efficiently. Another is the use of hybrid architectures, where a slower but rugged main computer handles critical functions, while a faster but more vulnerable coprocessor runs the AI, protected by error-correcting codes and periodic reboots. The European Space Agency has tested a deep learning processor called the Myriad that can be hardened for space, and NASA is experimenting with the use of machine learning accelerators on the International Space Station. But none of these systems are yet qualified for a deep space mission where the radiation dose is far higher and repairs are impossible. The bottleneck is not just hardware either. The software itself must be proven correct in ways that are unprecedented for AI. Terrestrial neural networks are often considered black boxes, their internal reasoning opaque even to their creators. For a critical decision like whether to fire a thruster or abort a landing, you need a level of transparency and reliability that current AI does not provide. Formal verification methods which mathematically prove that a system will never make a dangerous choice are being developed, but they are still too slow and limited to apply to large neural networks. Until that changes, every autonomous decision will carry a shadow of uncertainty. The dream of a fully autonomous spacecraft, one that can explore distant worlds with the curiosity and adaptability of a human scientist, waits on the other side of this bottleneck. It is a problem that spans hardware, software, and trust, and solving it will require a generation of engineers who can think simultaneously about radiation physics, neural network design, and the art of building systems that can be proven safe. The outer solar system is calling, but the answer depends on whether we can teach our machines to think for themselves on hardware that is up to the task. Even the smartest spacecraft cannot outrun a piece of debris traveling at 7 kilometers per second. That is more than 10 times the speed of a bullet, and at those velocities, even a fleck of paint carries the energy of a bowling ball. The problem of orbital debris has been building for over 60 years, ever since the first satellite left Earth. Today, thousands of tons of discarded hardware circle the planet. Dead satellites, spent rocket stages, fragments from explosions, and shards from collisions. Each piece moves on its own path, and even a tiny fragment can cripple or destroy an active spacecraft. For any mission that must pass through low Earth orbit, the risk is real and growing. But the danger extends far beyond the orbital lanes we use today. As we build toward a spacefaring civilization, the volume of traffic will increase dramatically. Not just satellites, but cargo ships, crewed vehicles, fuel depots, and lunar shuttles will crowd the space around Earth. And the same debris that threatens a communication satellite also threatens a Mars-bound spacecraft during its departure burn. Avoiding a collision requires knowing where every piece of debris is, and that is a monumental challenge. Current tracking networks, operated by the military and space agencies, can only reliably monitor objects larger than about 10 centimeters. That leaves millions of smaller pieces invisible to radar, yet still capable of causing catastrophic damage. A bolt lost during a satellite deployment, a flake of paint chipped off by radiation, or a droplet of frozen coolant from a rocket nozzle. Each one is a bullet waiting for a target. The only way to protect a spacecraft from these unseen threats is to shield it. The International Space Station uses a system of layered panels called Whipple shields, which break up a projectile into a spray of smaller particles that spread the impact energy. But that design adds mass, and the shielding only works for particles up to about 1 centimeter. Anything larger punches through. For a deep space vehicle that must be light enough to reach Mars, carrying heavy shielding for the entire journey is impractical. So the ultimate solution is not just to dodge or absorb debris, but to clean it up. Active debris removal is a field that has seen proposals for decades but very little action. Concepts range from robotic arms that capture dead satellites and drag them into a disposal orbit, to nets, harpoons, and even lasers that could nudge debris into a slow decay. The Japanese company Astroscale has launched a demonstration mission called ELSA-D, which uses a magnetic docking plate to capture a target satellite. The European Space Agency plans a mission called Clear Space 1, which will rendezvous with a defunct payload adapter and bring it down together. These are small first steps, but the scale of the problem is staggering. There are over 5,000 dead satellites and spent rocket bodies in orbit, plus tens of thousands of fragments. Removing even the largest ones would require dozens of dedicated missions, each costing hundreds of millions of dollars. And the legal framework is unclear. Under international space law, a defunct satellite still belongs to the country that launched it. You cannot simply grab someone else's property without permission, even if it poses a hazard. So debris removal is not just an engineering problem, it is a diplomatic and legal one. Nations must agree on rules for who can remove what, who pays for it, and who is liable if a removal attempt creates more debris. As traffic increases in cislunar space, the region between Earth and the Moon, the challenge will multiply. The Moon's gravity and the Lagrange points will become busy highways for missions, fuel depots, and habitats. Without careful planning, we could litter that pristine volume with debris as well, turning a future gateway into a hazard zone. The solution will likely involve a combination of better tracking, smarter spacecraft design that allows for end-of-life disposal, and international agreements that make debris removal routine and funded. Some have proposed a traffic management system similar to air traffic control that assigns trajectories and ensures safe spacing. But that requires every nation and company to share data, which is a hurdle in itself. The debris problem is a slow-moving crisis, one that builds quietly with every launch. It does not make dramatic headlines until a collision happens, like the 2009 event when an active Iridium satellite smashed into a defunct Russian Cosmos spacecraft, creating over 2,000 new fragments. That single event increased the debris population by more than 10%. As we push toward a future with thousands of satellites, regular crewed missions, and permanent outposts, the cost of inaction will only grow. The bottleneck is not just technology, it is the collective will to treat space as a shared environment that must be maintained, not a dumping ground we can abandon. The first generation of spacefarers did not think about cleanup. The next generation will have no choice. The most dangerous hazard on a Mars mission may not be debris or radiation. It is the crew's own bodies slowly turning against them in the absence of gravity. Every system that evolved under Earth's constant pull begins to falter when that pull vanishes. Bones that once supported a skeleton against gravity start leaching calcium at a rate of about 1% per month. After a year in microgravity, a person could lose 12% of their bone density, enough to make their skeleton brittle and prone to fracture upon return to gravity or during landing on another world. Muscles that have never had to work as hard against resistance begin to shrink, especially in the legs and lower back. Astronauts on the International Space Station spend up to 2.5 hours a day exercising with specially designed resistance machines and treadmills that use bungee cords to simulate weight. Yet even with that rigorous routine, they still lose muscle mass and strength. The cardiovascular system also struggles. Without gravity pulling blood downward, fluid shifts toward the head, causing puffy faces and putting pressure on the eyes. That pressure can lead to a condition called spaceflight-associated neuroocular syndrome, which changes the shape of the eyeball and can permanently impair vision. Over half of long-duration astronauts have experienced some form of this vision change, and the effects can last for years after they return to Earth. The immune system also behaves oddly in microgravity. White blood cells become less active, and latent viruses like the one that causes shingles can reactivate without symptoms. This leaves the body more vulnerable to infections that could spread quickly in a closed habitat. The list of known changes is long and still growing, but what concerns researchers most is what they do not yet know. No human has spent more than 14 consecutive months in space, and that record belongs to Valery Polyakov aboard the Mir space station in the mid-1990s. A round trip to Mars, even with efficient propulsion, would stretch beyond that to about 2 to 3 years, and beyond Mars to Jupiter or Saturn, the mission would last half a decade or more. The long-term effects of that duration are simply unknown. We have no data on how the human body responds after 2 or 3 years of continuous microgravity, or after the sudden transition back to gravity on another world. The countermeasures we have today, exercise devices, nutritional supplements, and drugs to slow bone loss, are blunt instruments. They slow the damage but do not stop it. Artificial gravity, long considered the ideal solution by spinning the spacecraft, brings its own engineering complexities, as discussed earlier, and even if we spin the ship, the crew would still need to tolerate the Coriolis forces and the mechanical wear of a rotating structure. The pharmaceutical approach is advancing. Researchers are testing bisphosphonates, the same class of drugs used to treat osteoporosis on Earth, to reduce bone loss in orbit. A study on the ISS found that astronauts who took a bisphosphonate experienced significantly less bone density decline. But these drugs have side effects, and their long-term safety in the harsh space environment is not fully known. There is also interest in gene therapies or synthetic hormones that could trick the body into maintaining its Earth-adapted state, but those treatments are far from flight-ready. The deeper problem is that every countermeasure adds mass, power, and complexity to the mission. Every kilogram of exercise equipment, every gram of medication, every extra kilowatt for a spinning centrifuge must be lifted from Earth. And for a multi-year mission to the outer planets, those resources compete directly with propulsion, shielding, and life support. The human body is a fragile, exquisitely tuned machine, and microgravity is a slow dismantling of that tuning. We can slow the process with exercise, drugs, and spinning, but we do not yet have a complete solution. The mind, too, faces its own challenges in confinement and isolation, but that is a different kind of wall. For the body, the wall is real and measurable, and it may be the ultimate limit on how far we can go and how long we can stay. The quietest bottleneck of all is the one inside our own skin. The mind does not atrophy as visibly as bone, but it can break just as surely in the quiet emptiness between worlds. On Earth, the human brain is constantly fed by a rich stream of sensory information. The sound of wind, the sight of trees moving, the feel of a breeze, the presence of other people within a few meters. In deep space, that stream becomes a thin trickle. The habitat walls are the same every day, the corridors are narrow, the air circulates with a constant low hum. Outside the viewport, there is only blackness and the distant, unchanging stars. After months of this, the mind begins to crave novelty. and the lack of it can erode motivation, focus, and emotional stability. The most famous experiment in this field is Mars 500, a Russian-led study that locked 6 volunteers inside a mock spaceship for 520 days, the exact duration of a simulated Mars mission. The crew lived in a windowless facility in Moscow, cut off from the outside world except for a delayed communication link that matched the real-time lag to Mars. The results were sobering. While the crew completed the mission, many experienced periods of low mood, increased irritability, and social tension. One participant described a growing sense of monotony that made even simple tasks feel exhausting. Sleep patterns shifted, and some crew members withdrew from group activities. The study showed that even highly motivated, carefully selected individuals can struggle with the psychological weight of long-term confinement. Another analog, High Seas, run by NASA on the slopes of Mauna Loa in Hawaii, placed small crews inside a dome on a barren lava field for months at a time. The isolation was real, but the communication delay was minimal, unlike deep space. Even so, crews reported conflicts over small issues like cleaning duties and noise levels. One crew cut their mission short after a member experienced a personal crisis. These studies underscore a crucial insight. The biggest threat to a deep space crew may not be a technical failure, but a breakdown in human relationships. To prevent that, habitat design must become a tool for mental health. The layout of the ship or base can encourage social interaction while also offering private retreats. Color, lighting, and texture matter more than most people realize. A sterile white hallway can feel oppressive after a year, while warm earth tones and adjustable lighting can mimic the cycles of day and night that our brains evolved to expect. Windows, even if they show only the stars, provide a vital connection to the outside world, and the ability to create personal spaces, a place to hang a photo or arrange a few objects, helps maintain a sense of identity. Crew selection becomes equally critical. Not everyone has the temperament for years of close quarters with the same faces. Psychologists look for traits like emotional stability, low need for stimulation, and a high tolerance for ambiguity. They also assess how individuals handle conflict and whether they can remain cooperative under stress. A crew that gets along well in a 2-week training simulation may not survive a 2-year mission without friction. Some researchers have proposed building crews of 4 rather than 6, because smaller groups reduce the number of social interactions and the potential for alliances or factions. Others advocate for mixed-gender crews, which tend to have better social dynamics, though that also introduces its own complexities. The most forward-thinking idea involves virtual reality. Imagine a crew member on a 9-month journey to Mars. They have seen every corner of the ship, talked to the same faces hundreds of times, and the next supply pod is not coming for another year. A VR headset could transport them to a forest, a beach, or a city street, providing the sensory variety that the real environment cannot. Even a simple simulation of walking through a park could reset the mood and reduce stress. Studies on Earth have shown that VR nature experiences lower cortisol levels and improve mood, even in isolated settings like Antarctic research stations. On a spacecraft where every kilogram counts, a lightweight VR system could be a small investment with a huge return in crew mental health. The same technology could allow crew members to interact with family and friends back home in a more immersive way than a flat video call. Instead of staring at a screen, they could sit in a virtual living room together, sharing a space that feels more connected despite the minutes-long delay. But VR is not a cure-all. It requires power, storage for content, and maintenance, and if used too much, it could deepen the sense of unreality, making the real habitat feel even more confining. The balance is delicate. The deepest challenge may be the one that cannot be engineered away. the awareness that you are millions of kilometers from the only place humans have ever called home. That existential loneliness does not show up in a sim study, but it will be a constant companion on any long voyage. How crews cope with that will depend on their training, their relationships, and the stories they tell themselves about why they are there. The psychological bottleneck is not about preventing every moment of sadness or frustration. It is about building a system that can sustain a healthy mind through years of silence and stillness, so that when the crew finally steps onto another world, they are intact enough to appreciate it. Every one of these challenges eventually runs into the same wall: the cost of lifting a single kilogram off Earth. For decades, that price tag hovered around $10,000 per kilogram to reach low Earth orbit on an expendable rocket. A mission to Mars or beyond multiplies that many times over, because you need not just the payload but the fuel, the shielding, the life support, and the structure to hold it all. Launch costs are the gatekeeper of the entire space enterprise. They decide what is possible and what remains a dream. The arrival of reusable rockets, pioneered by companies like SpaceX, has cut that gatekeeper down significantly. A Falcon 9 launch now costs roughly $2,500 per kilogram, a fraction of the old price. Starship, if it achieves full reusability, could push that number below $100 per kilogram. That would be a revolution, but even at that low price, the total cost of a crewed Mars mission still runs into the tens or hundreds of billions of dollars. The reason is that launch costs are only one piece of the puzzle. The spacecraft itself, the life support systems, the radiation shielding, the landing gear, the surface habitat, the return vehicle, all of those must be designed, built, tested, and certified. That upfront development cost dwarfs the launch price. A single heavy lift rocket might cost $100 million to launch, but developing a new engine or a closed-loop life support system can cost billions. And because there is no mass production for deep space hardware, each component is built by hand, inspected carefully, and qualified for a single mission. The economies of scale that drive down the cost of cars, smartphones, and aircraft simply do not exist in the space industry. A car factory can produce 1 million identical units, spreading the cost of research and tooling across an enormous number of sales. A Mars spacecraft factory, if such a thing ever exists, might produce one vehicle every few years. That means every engineer hour, every test fixture, every specialized tool is amortized over a tiny number of products. The result is that even a simple component can cost a fortune. Consider a valve. A standard industrial valve might cost a few $100s. A space-rated valve, built to withstand extreme temperatures, vacuum, vibration, and radiation, with redundant seals and rigorous testing, can cost tens of thousands of dollars. Multiply that by the thousands of components in a spacecraft, and the price climbs astronomically. The only way out of this spiral is volume. If hundreds of starships are built and launched regularly, the cost per vehicle plummets. If dozens of Mars missions are planned over a decade, the development costs can be spread across many flights, but that requires a market large enough to justify the investment. And that market does not yet exist. Today, the primary customers for space are governments and a handful of satellite operators. There is no commercial demand for Mars transportation because there is no economic activity on Mars to support it. The chicken and egg problem is stark. Without cheap access to space, you cannot build the infrastructure that would create demand. Without demand, you cannot justify the investment to make access cheap. Reusable rockets have cracked the first part of that cycle for Earth orbit, but the second part in space remains locked. Fuel depots, orbital assembly yards, and asteroid mining operations all require enormous upfront capital with a return that may take decades. Private investors are understandably cautious. Governments can absorb that risk, but they move slowly and are subject to changing political priorities. A spacefaring civilization will require a fundamental shift in how we fund and build space infrastructure. It may require new models like public-private partnerships where the government guarantees a market for certain services. It may require international consortia that pool resources across nations. It may require entrepreneurs who are willing to bet everything on a vision that will not pay off in their lifetime. The economic bottleneck is not a problem that can be solved with a single invention. It is a slow, grinding process of building the markets, the factories, and the trust that make large-scale space activity possible. And every step forward depends on the step before it. The cost to orbit comes down, so we build more satellites. More satellites create demand for cheaper launch, which drives further innovation. That virtuous cycle is just beginning to spin, but it has not yet reached the point where a mission to Mars or an asteroid mine becomes a rational business proposition. Until it does, the economics of space will remain the most stubborn bottleneck of all, a quiet reminder that even the best engineering cannot defy the laws of money. A treaty written in the age of Apollo still governs every claim beyond Earth. The Outer Space Treaty of 1967 was a remarkable achievement for its time, a document that set the rules for a domain that no nation could truly own. It declared that space is free for exploration and use by all, that no country can claim sovereignty over any celestial body, and that weapons of mass destruction cannot be placed in orbit. Those principles have served well for decades, but they were written when human activity beyond Earth meant a handful of robotic probes and a few brief footprints on the Moon. They were never designed for lunar bases, asteroid mining operations, or a permanent settlement on Mars, and now those possibilities are approaching faster than the law can adapt. The treaty explicitly prohibits national appropriation of celestial bodies, but it does not clearly address whether private companies can extract resources and sell them. That ambiguity has created a legal gray zone. If a company lands on an asteroid and begins drilling for water or metals, does it own what it takes? The treaty says no nation can claim the asteroid, but it does not say a corporation cannot. The answer may seem obvious to engineers and entrepreneurs, but to lawyers and diplomats, it is a wide-open question. Without clear property rights, investors hesitate to put billions into a venture that could be challenged in court or by a foreign government. The same uncertainty hangs over any lunar base. A habitat built in a crater near the South Pole has no legal protection against interference from another nation's lander. There is no space police, no interplanetary court to resolve disputes. The only recourse is diplomacy, which moves slowly when it moves at all. The Moon Agreement of 1979 tried to clarify some of these issues by declaring the Moon and its resources the common heritage of mankind, implying that any extraction would need international oversight and benefit sharing. But only a handful of nations ever signed it, and the major spacefaring powers, including the United States, Russia, and China, stayed away. The agreement is effectively dead, leaving a legal vacuum. In recent years, the United States has taken a proactive step with the Artemis Accords, a set of bilateral agreements that outline principles for cooperation on the Moon and beyond. The accords affirm that resource extraction is allowed, that safety zones can be established around lunar operations to prevent interference, and that all activities must be transparent. They are a start, but they are not a global treaty. They only bind the nations that choose to sign, and key players like Russia and China have not joined. The risk of conflict or misunderstanding grows as more actors enter the same small patches of valuable lunar real estate, particularly at the poles where water ice is concentrated. A Mars colony would face even greater legal complexity. On Mars, there is no agreed-upon authority to grant land, enforce contracts, or settle disputes. A colony would need its own legal system, but under whose authority? The Outer Space Treaty forbids national appropriation, but a city of 1 million people cannot operate without laws. Some scholars have proposed that Mars settlements could be governed by a new framework, perhaps modeled on international law for Antarctica or the high seas, but those analogies are imperfect. Antarctica has no permanent population, and the high seas have a flag state system that assigns responsibility to the vessel's home nation. Neither translates well to a self-sustaining colony on another world. The bureaucratic bottleneck is not just about writing rules, it is about building the institutions that can enforce them, adapt them over time, and resolve conflicts peacefully. That requires a level of international cooperation that has been rare in human history. It requires nations to trust each other with access to strategic resources and to agree on standards for safety, environmental protection, and liability if something goes wrong. A mining accident on an asteroid could create debris that threatens other spacecraft. A failed habitat on the Moon could become a hazard for future missions. Who pays for the cleanup? Who investigates the cause? The legal framework for these questions barely exists. Without it, investors remain cautious, and mission planners must account for a level of uncertainty that no engineering solution can fix. A political bottleneck is not a physical wall or a missing material. It is a collection of papers, treaties, and negotiations that have not yet been written. And until they are, every moon base, every Martian settlement, every asteroid mining venture will carry a hidden risk that the rules of the game could change overnight, or that no rules exist at all when they are needed most. That uncertainty is a barrier as real as the rocket equation, and it will take diplomats, lawyers, and politicians working alongside engineers to tear it down. The first human footprints on Mars may be just a decade or two away, but the legal foundation to make that settlement permanent and peaceful is still being sketched in draft proposals and diplomatic cables. One day, those papers will be as important as the rockets themselves. Apollo was a single nation, a single goal, and a single budget that dwarfed everything else. Today, the landscape looks nothing like that. We have NASA planning lunar bases, the Chinese space station growing module by module, SpaceX building a rocket that could reach Mars, the European Space Agency working on sample return missions, and a dozen private companies launching constellations, habitats, and landers. It is a dynamic, exciting, and deeply fragmented ecosystem. Each player pursues its own timeline, its own engineering standards, its own financial model, and its own political mandate. There is no central command, no unified roadmap, and no shared agreement on what comes next. The result is duplication of effort, incompatible hardware, and missed opportunities for collaboration. A spacefaring civilization, one that truly expands beyond Earth, will likely require something that we do not yet have: a networked approach that shares research, development costs, technical standards, and risk across multiple nations and companies. The Apollo era proved that a single focused push can achieve extraordinary things in a short time, but that model only works for a finite goal like landing a few people on the Moon. Building a permanent presence on another world with mining operations, fuel depots, and settlements is an open-ended endeavor that no single nation can sustain alone. The International Space Station showed that cooperation is possible, but it took decades of negotiation, and it remains an exception rather than the norm. Today, geopolitical tensions make that kind of coordination even harder. Differences in priorities, security concerns, and competition for prestige and resources keep the major spacefaring powers from pooling their efforts. Imagine what could be accomplished if the resources poured into competing rocket programs were combined into a single heavy lift system. If the expertise of different space agencies were merged into a shared life support development. if the legal frameworks for lunar resource rights were agreed upon before the first drill touches the regolith. That vision is not a fantasy, but it requires a level of trust and long-term thinking that is rare in international politics. The bottleneck here is not a missing technology. It is the human capacity to set aside short-term rivalry for a shared future among the stars. And until that capacity matures, the dream of a true spacefaring civilization will remain splintered, with many small steps forward but no giant leap that belongs to everyone. Every bottleneck we have discussed shares a common root: the absence of a permanent space infrastructure. We have brilliant engines, clever life support concepts, and promising materials in the lab, but none of them are connected into a working system that can sustain repeated travel beyond Earth. Think of any major city on our planet. It has roads, power grids, water pipes, fuel stations, repair shops, and warehouses. These elements support each other, allowing the city to function and grow. Remove one layer, say the fuel supply, and the entire system grinds to a halt. Right now, in the vast volume between Earth and the Moon, there is nothing like that. There are no fuel depots waiting with full tanks, no space tugs that can move a cargo pod from low orbit to a lunar transfer trajectory, no dry docks where a damaged spacecraft can pull in for repairs, no permanent habitats where crews can rest, resupply, or wait for the right launch window. Every mission must carry everything it needs from the beginning, and that single fact multiplies the mass, cost, and risk of every endeavor. The infrastructure gap is the reason we can send a rover to Mars but cannot yet send a human. It is why a lunar base remains a plan on paper rather than a construction site. Building that infrastructure is a chicken and egg problem that loops back on itself. A fuel depot in orbit would slash the mass needed for a Mars mission because the ship could refuel after launch instead of carrying all its propellant from Earth. But to build that depot, you need a way to transport fuel from Earth cheaply and store it in space without boiling away. That requires advances in cryogenic storage, orbital transfer vehicles, and high-volume launch systems, all of which are bottlenecks we have already discussed. A space tug that can push cargo between orbits would allow supplies to reach a lunar base without each item needing its own landing engine. But the tug needs a power source, propellant, and a navigation system that can operate autonomously for months. Those are the same propulsion, power, and autonomy bottlenecks we have seen. A dry dock where astronauts can repair a spacecraft would demand a large pressurized volume, robotic arms, and a steady supply of spare parts. That requires habitation technology, materials manufacturing, and logistics, again the same unsolved problems. Each piece of infrastructure depends on breakthroughs in several other areas, and those breakthroughs themselves depend on having the infrastructure to test them at scale. The result is a trap. You cannot build the fuel depot until you have cheap launch, but cheap launch alone does not solve orbital storage. You cannot build the space tug until you have high-efficiency propulsion, but high-efficiency propulsion needs a way to be refueled. You cannot build the dry dock until you have reliable habitats, but habitats need the docking and servicing capabilities a dry dock would provide. This is why space agencies and private companies have focused on individual missions rather than systemic infrastructure. A single mission to Mars, even a risky one, is a well-defined project with a beginning, middle, and end. Infrastructure is a continuous investment with no clear payoff date. Investors and governments prefer the concrete milestone of a landing to the abstract promise of a depot. Yet without that infrastructure, every mission remains an expedition, not a migration. We plant flags, but we do not build cities. The way out of this loop is not to solve every bottleneck in isolation. It is to pick a few critical pieces and build them together, understanding that they will be imperfect at first but will improve over time. The first fuel depot might be a simple tank that leaks a little propellant and requires frequent resupply. but it proves the concept and drives demand for better storage. The first space tug might be a slow ion thruster that takes months to shift cargo, but it demonstrates the utility of orbital transfer and justifies investment in faster engines. The first dry dock might be a repurposed habitat module with a robot arm, crude but functional, and it teaches engineers what needs to be redesigned for the next version. The pattern is familiar from every frontier in human history. The first settlements in a new land did not have roads, ports, or hospitals. Those were built step by step by people who started with a single shelter and a small boat. The same will happen in space, but the scale and cost are so immense that the steps must be carefully chosen. The infrastructure bottleneck is not a single missing invention. It is the absence of a coordinated effort to build the scaffold that will hold the future. And that effort requires a willingness to accept early, imperfect systems, to invest in long-term capability over short-term spectacle, and to recognize that a fuel depot in orbit is worth more than a dozen flags on the lunar surface. The footprints we leave on another world will only matter if we have the infrastructure to stay. Propulsion burns fuel, radiation bombards cells, life support recirculates precious molecules, and cost keeps the whole enterprise tethered to spreadsheets. Each of these bottlenecks looks like a wall, but not one of them is unbreakable. The rocket equation is a law of physics, but we can work around it with orbital refueling, nuclear thermal engines, and eventually fusion. Radiation is a hazard, but clever shielding, active magnetic fields, and faster transits can reduce the dose to acceptable levels. Life support struggles to close its loops, but bioreactors and smarter recycling are advancing steadily. Cost remains the most stubborn barrier, but reusable rockets and expanding commercial markets are driving it down year after year. None of these problems requires a miracle. Each one demands patient, sustained engineering, decade-long research programs, and a willingness to accept incremental progress over flashy breakthroughs. The real shift is not technological. It is a shift in mindset. For 60 years, we have treated space as a destination for brief visits, flags, footprints, and sample returns. The next step is settlement, and settlement changes everything. It means building for permanence, not for a single mission. It means designing systems that can be repaired, expanded, and handed off to the next crew. It means thinking in centuries, not election cycles. That change does not happen in a single laboratory or space agency. It happens in the way we educate the next generation, in the choices we make about funding research, in the stories we tell about why space matters. The viewers watching this video are part of that story. Every student who chooses engineering, every citizen who votes for science funding, every person who learns the names of the moons and the distances between them, is contributing to a culture that will one day cross those distances. The bottlenecks we have discussed are real, but they are not permanent. They are challenges waiting for enough minds to focus on them. The future among the stars will be built by those who understand that the hardest problems are also the most rewarding to solve. And it begins not with a rocket launch, but with a single question: what do we want to become?